investigation. I had you guys use the square root function because you've studied a bunch of functions, but the cool thing about the square root is like it reflects one way, it looks totally different. When it reflects a different way, it looks totally different. And you can't say that for all the functions. Like a parabola doesn't look any different when you reflect it a certain way. It just looks the same as it did. So I tried to pick a function where you guys could see like a starting point and the difference in the reflection. So that's kind of why we did square root. It's not any more or less important than any of the other ones. Okay. And then what you should have noticed about the parent equation is that that b value is something you haven't dealt with before. And so we're going to have to try and think about the way we format our equation each time we look at it. So when you guys went and looked at the different functions, so A, H, and K will go a little bit faster through only because you have done them before, but you can treat this like the end. At the end, we will go and write stuff down. So right now, you can just focus up here and answer questions, and then I'll write down the things I think you should write down at the end, or you can summarize them how you want. So when we were looking at the A value, okay, there was kind of two things to pay attention to. First thing is when A is negative, versus, so this is positive A and then negative A. Okay. So when you change A from a positive to a negative, what happens on the graph? Okay, it reflects, is what Josh said. In over what? What is it reflecting over? Okay. The x-axis, right? Okay. So A reflects over the x-axis. Then there's a matter of the value of A. So I'm going to turn A back positive here. So here it is at 0.6. Here it is at 1.1. Oh, sorry. Here it is at like 3.8. What happens as I make the A value larger in the number? Danielle? Okay, good. It stretches. And before that was probably enough for you guys to say because you didn't have the B value. But do you guys know which direction it's actually stretching your graph? Is it stretching it vertically, like changing the y's, or horizontally and changing the x's? Vertically and changing the y's, okay? That's going to be really important for us now because we want to understand that A is a vertical change. It's stretching and compressing things, but specifically in the vertical direction. We've studied that before. So we see when A gets bigger, it gets more stretched out. If A gets smaller than 1, it starts pushing it back towards the axis, and we called that a compression. Okay? So A can reflect over the x-axis, or it can cause a vertical stretching or a vertical compressing. Is that okay with everybody? And we'll write it down in a little bit, but are these words familiar to you, and do you feel like you can see that in the picture? Right? So then you guys looked at H. What was H responsible for as you moved it across the graph? Olivia? Good. It shifted it left or right. Okay, Kenna?
Or it meets the x-axis, it's stuck.
Good. So if we don't shift it up or down, it also will be exactly where it meets the x-axis, or at least that value, even if we do shift it up or down, since it does shift it left and right, will be the x-coordinate of like our starting point of our graph. Okay. What about the k value? When you guys moved the k value, who can describe what sort of transformation you saw with this? Okay, so we moved it. Here's negative. Here's positive. What's happening to the graph when we change the number that's in that spot that represents the k value? Will?
I said the k value affects the y-axis and will determine whether the k value will be negative or positive on the y-intercept.
Good. So if we don't shift it left or right, it will help determine our y-intercept, okay? Negative or positive. But even if we do shift it left or right, it does change that y value still, and that y value will show up again at our vertex or our starting point of the function. Is that okay with everybody? All right, so H was left and right shifting. K was up and down shifting. A is a little more complicated. Positive, negative can cause reflecting, and the numbers can cause stretching or compressing, right? So now let's talk about the new part of the function we're looking at, which is the B value. Okay? So we're going to look at B the same way we looked at A. Does anybody have any idea why I'm kind of grouping A and B together? Why would they be similar? Like, how do they show up in the equation that would make them similar? Danielle?
They do the same thing, just in reverse.
Good.
With the values.
Good, and good observation. So they're doing like the same thing, right? When I move B around, I see flipping and I see like stretching and compressing. The hard part here is understanding the direction. So in your equation, B is inside the radical. Do you guys see that? It's inside there with X, kind of like H was. K and A were outside of the radical. The things outside of the radical were doing vertical things. The things inside the radical, like H, are supposed to be doing horizontal things. So B, because it's inside the radical immediately affecting X, is also going to be something that we want to view from a horizontal perspective and how it's changing things horizontally. Okay? And then we're going to look at it like A because it's also multiplying stuff. So we're going to look at what happens when it's positive versus negative, and then what happens when it's like a smaller number close to 0 or a bigger number bigger than 1. So watch what happens when B becomes negative. So it's positive, and now it's negative. So what happens if the B value is negative? What type of transformation? McKenna? A reflect over the y-axis. Are you guys okay with that? So when B is positive the whole time, our curve stayed over here. And then when B is negative, the curve is now working over here. So it's flipping this way. And it might be kind of weird for you guys that we just said reflection over the y-axis and I just told you it was horizontal. And sometimes our people are like, no, you can't say y if you're talking about horizontal. But remember, if you're changing horizontal stuff, you're changing x's. Look at the x's on the graph. Here's all the positive x's, right, on this side of the graph. If you change the sign of those, you make all the positive x's negative, they move from the right side of the graph to the left. If you change all the negative ones positive, they move to the right. So you are changing x. You are changing the horizontal thing. But when you change x's, you actually flip over y. Okay? When we were using the a value, we were changing the y's. But when you change the y's, you actually flip over x. Is that okay with everybody? All right. So this is still a horizontal thing. It's changing x's, but this change in x's causes us to say reflection over the y. It's changing on top of the y-axis. Okay. All right. Now let's look at the numbers. So I'm going to bring it back to the positive. Okay. So here's like numbers smaller than 1 and then numbers bigger than 1. So right now, I'm going to put it here, and I'm going to scroll it over, and I want you guys to tell me whether I'm stretching or compressing the graph when I move in a certain direction, okay? So here I go. Okay, we want to say stretching, and you guys would be right if we were looking at it from a perspective of vertical stuff. With vertical stuff, it'd like I'd be grabbing it and pulling it up like this. Is that okay with everybody? But I want you to watch again. And I want you to think about it in a horizontal direction because B is supposed to be a horizontal change. When you're watching the graph change, think about me holding on to the x-axis. Am I horizontally pulling it apart and stretching it? Or am I horizontally pushing it all closer to the y-axis? Okay, so watch again. So what's happening horizontally? Are they getting pushed back to the y-axis or stretched far away from the y-axis? Pushed back. So actually, as the B number gets bigger, it's kind of weird, in the horizontal world, the graph is actually getting compressed and pushed back because we're talking horizontally, not vertically, okay? And then as B gets smaller, so I'll move the other way. So we just said if B gets bigger, we're actually pushing it together and compressing it horizontally. So then the opposite should happen when I move the other way, right? So I'm going to make B smaller again, and what you should see is it's like someone's taking the graph and now stretching it out this way, okay, horizontally. So see if that looks about right. Okay, do you see that effect like someone's pulling it here? So a hard part about this B value is going to be wrapping our mind around the fact that the number got bigger, but we actually have to say the word compression. And when the number is getting smaller, we're actually saying the word stretch because we're looking at it from a horizontal perspective and not a vertical perspective. Okay, and I'll show you another reason why that is the way it is if your head is like, I need some connection. And we'll also write it down very specifically so you have the right information in your paper. But does that at least give you an overview that like B is kind of like A, but we're looking at it from a different perspective and it changes kind of the idea a little bit, okay? So we're going to go in your note guide and write down these things. If you don't have your note guide, you basically just want to set it up like this. You want some idea, some chart where you can refer back to what A, B, H, and K do. I know you just studied a square root function, and right here I wrote a cubic function, but something you should have taken with you from Algebra 2 was that A, H, and K did the same kind of transformation. No matter what you were using, you just had to start with a different graph, okay? All right, so we said that A could do two different things. So try and think about what we just talked about, what you know from Algebra 2. What are the different transformations that A can do? And when I say transformations, there's three different worlds, like reflecting, translating, which is like shifting, or stretching / compressing, okay? So those are the things that we're mentioning. So what is one thing that A is in control of? McKenna? Okay, so A can cause a reflection. Are you guys all okay with that? We said that that could happen. So one of the things that A can do is it can cause a reflection. And then I want you guys to remember that we said A and K were vertical things. Meaning they control measurements about the y coordinates on the graph. But again, if you reflect y coordinates, so I'm just going to draw a little mini picture off to the side. If I had a point whose y coordinate was above the x-axis and then I reflected it, I changed the y from a positive to a negative, it ends up down here. So even though I'm changing the y, the reflection is actually over the x-axis. So A can cause a reflection over the x-axis, and that happens specifically when A is less than 0. If you don't like seeing that in your notes, like that notation, A is less than 0, what would you write down to say what I'm talking about A? If A is less than 0, what am I saying about A? It's negative. Okay, so if that sits better with you, then write when A is negative. Okay? All right, so one thing A controls is the reflection. The reflection is only if it's positive, it's not reflected. If it's negative, it is reflected over the x-axis. Okay? But A controlled something else as well. So what was the other type of transformation that we saw that A controlled? And I see McKenna's hand, but I'm not letting you guys all off the hook. So again, there's only three answers when I say what kind of transformation, either reflections, translations, or shifting, or stretching / compressing. Griffin? Good. A also controlled stretches and compressions, and in which direction? Were we pulling the graph vertically or horizontally? Vertically, right? Look at what I circled at the top. The stuff outside of the cubing, the stuff that would happen after you're done cubing would happen to the y coordinate, not the x coordinate. And so it falls into two categories. I'm going to write the categories, and if you don't like the notation, we'll talk about it. So first of all, I put absolute values around my A's. Don't let that bother you. What does absolute value do to numbers? It makes it positive, right? So what I'm saying here is that I don't care if A is negative or positive. Like, just look at the number part of A. If the number part of A is smaller than 1, so it's like a half, 0.2, 1/3, 2/3, those smaller numbers are bringing A smaller and closer to the x-axis. They are a vertical compression. They do exactly what you think they would do. They make the vertical distance less. So if you used to be 10 units away and I do a compression by a half, that point gets squished to only 5 units away from the axis. Kind of like they take the y-axis, squish it all back towards 0. Okay? When the A is bigger than 1, so you see an A like 5 or even -10, because we're not talking about if it's negative or positive, just the number part, that's where you're seeing a vertical stretch, like someone's grabbing the y-axis and stretching out the graph that way. right? And let's do the other vertical thing while we're here so that we can really kind of sort it in our head that the vertical things are affecting the y's. So if you even want to write a note next to vertical, that this is changing the y coordinates of the graph. Okay? So A controls one aspect of it, reflecting it or stretching and compressing it. And K is the other thing that was vertical. What did K do to our graphs? What did we say when we looked through that investigation? Josh? Good. Okay, so K basically shifted or translated our graph up or down. Okay. So this shifts our graph up or down. Right, and then we're going to look at everything that's kind of stuck inside of the function. When I say the words inside of the function, I'm referring to the fact that in this case, the function is a cubic, and this group of stuff is inside the cubic and would all be done if you were doing like order of operations before you ever got to the cubing. So these things are going to be horizontal changes, meaning they're going to mess with like the x values instead of the y values. And you can see that because all that stuff is grouped around x in the function. Okay, that's how you can kind of decipher horizontal versus vertical. So first, the h value, because that's what you guys are familiar with. What does h control about the graph? So someone new that hasn't told us yet. Aaron?
Shifts left to right.
Good. Okay, so h shifts left or right. And it's a little tricky, and we'll make a note at the bottom about really identifying the correct h value in a minute. And then now we're going to talk about the b value. So just like the a value, what we saw is that the b value can control multiple aspects of our function. So what is one type of transformation that the b value can control? What can it cause to happen? So remember, types of transformations. Good. So one thing it can do is it can also cause a reflection. And again, if you guys struggle over which axis, remember B is a horizontal change. So if I drew the same like silly little picture and I had this point over here, this point right now would have a positive x coordinate, right? If I'm going to change the x coordinate with a negative, it would move this point over here. It would change from a positive x to a negative x. So I am changing x. But when I'm changing x on the graph with its sign like that, it actually moves the point from one side of the y-axis to the other. So over the y-axis. So in my head, when I struggle with which axis to write down, I ask myself, does B change the x or the y? And I go, oh, it's horizontal. It changes the x. When I change the x on the graph from negative to positive, what am I flipping over? And that's how I know to write down over the y-axis. Okay? And then what else can B control? What other types of transformations did we see happen to the graph when we moved the little thing back and forth and saw what B could do? Okay. Good. So it also does stretching and compressing. So it can cause a horizontal compression or a horizontal stretch. But here's where it got a little bit tricky. What was happening to the B value on the graph when it was actually horizontally stretching it? What was I doing to the B value? Making it smaller or bigger? I was making it smaller when it was like the graph was getting stretched out. And then when I was sliding it bigger, it was like the graph was getting pushed in from the horizontal direction. It's a little confusing because a horizontal compression looks like a vertical stretch. So we have to kind of keep track of that. So this is the opposite of what you see happening with A. If the B value, if you want it to compress, you actually have a bigger number in the equation is causing the compression. So when B value is bigger than 1, it's causing the compression. And when B value is smaller than 1, it's causing the stretch. And again, those absolute value bars are there just saying, I don't care about the negative or positive. That's whether or not there's a reflection. Just look at the number part for me to determine what's happening. Okay? And then I'm just going to give you guys a quick idea to kind of wrap your head around the B value a little more and make sure you can pick out your H properly now that we've put B into the equation. So let's say that I gave you guys something similar to what you had. Sure. we'll do this. So you guys saw this in your investigation. Not this exact equation, but this part of it looked the same inside the radical. So a lot of people's first inclination was to say that h was equal to 6 or to -6 because the 6 was sitting here. Okay? You're good. So when we look at this, we do see a 6 in the h spot. But here's the thing. You guys have only studied h like this before. No number in front of x except for 1. If you've only studied it that way, you only know what the function is doing when it looks exactly like that. Meaning if you want to find h every single time, you need to have a group in your equation that is just x minus h, not 6x minus h, not 1/3 x minus h, just x minus h. So whenever you see something in front of x like this b value, you need to separate the b value, which in this case would be 2, from a quantity that can be your x minus h. So when I factor a 2 out of this, the first term is x. That's what I want because I want it to look like this. And then I need to see what's left. What would be the rest of this quantity here? X plus 3. So now I should see that my h value has something to do with the number 3, not the number 6. Does that make sense to everybody why we're not using 6? Unless you want to go study x minus h, 3x minus h, 2x minus h, a half x minus h, which I don't recommend. You just need to rearrange it like this every single time, okay? Now, is h 3 or is h -3? Good. So h is actually -3 because remember the formula says x minus h. So you're trying to figure out what would be the h with the minus already part of the formula so that when you write that h value here, in the end, it ends up looking like what you have in your equation that says x plus 3. If I put a 3 in here, that does not look like x plus 3 if h is +3. It actually looks like x minus 3. But if I put a -3 as h, that minus the negative would make it look like a plus, and I would have an h value of -3. So is everybody okay with picking out the b and the h value correctly? All right, and then one more explanation of why b is doing what it's doing. It's super weird, okay? In this equation, if I was to write out the transformation, see how the b value is a 2, right, and the one we're working on right now? My b value is a 2. So I should know that I'm either going to say horizontal stretch or I'm going to say horizontal compression. And I need to know like by how much, like are they stretching it out 5 times bigger, 8 times bigger, or are they shrinking it down 1/3 or 1/2, okay? So if you look at the directions we just wrote down and your b is a 2, okay, it's a number bigger than 1, what are the words that we would say? Horizontal compression. Weird, right? I get it. Just like h is -3 and it's not +3, all the horizontal stuff is whack. Okay, that's because it means one thing in an equation and a different thing on your graph. I'll try to give you guys some perspective. What this means in our equation, I'll show you guys. I will compare this to this. And I know this is a little bit deep mathematically. It's a little bit hard. Okay, so our parent function for a square root looks like this, 0, 1, 4, 9. If you don't remember it, don't worry. We're going to go back through it. But it looks like this. If we make this same chart for a 2 right here, I still get 0, 0. If I plug in 1, I can't calculate, so I'm not going to use 1. If I plug in 1/2, I can calculate it. 1. If I plug in 2, I can calculate it. 2. If I plug in 1, I want to get 9, so like 9/2 gives me 3. All right. Here's the chart for the new one. I'm okay if you can't make the chart, if you just believe me that this is a chart of points for one and this is a chart of points for the other. Here is what I want you to look at. In the parent function, how many x's did it take to get from the beginning of the parent function to a y value of 2? It took, how many x units over on the graph would you have to go before you reach a y of 2? 4 units, right? Look at the new chart. How many x's do you have to go over on the graph to reach a y value of 2? 2. Okay? So when I put a 2 in here, here's basically what the equation is saying. Guess what? X can reach that y value twice as fast as it used to. Did you guys hear what I said? So the 2 means that X can get to the y values twice as fast as it used to. But we don't graph how fast X is moving. We graph how long X takes. If you drive to school twice as fast as you normally do, how long does it actually take you to get to school compared to your normal time? Half as long. So moving twice as fast means it only takes me half as long. Does that make sense to everybody? So the 2 in the equation is meaning something like twice as fast, but we don't graph how fast, we graph how long, and so we want to graph half as long. So basically with B, if you want to make a little note for yourself, every time you see a B, you actually want to use the reciprocal, okay? Meaning 2 is the number in the equation, but what am I going to actually use when I'm calculating my points on my graph? The reciprocal of 2, which is a half. Does it make sense now if I'm actually using a half, why we are saying the word compression horizontally instead of stretch? Okay? If it wasn't a 2 in my equation, let's say it was a 10 in my equation, I would be using 1/10, which would still be a horizontal compression because 1/10 makes things smaller. In my equation, let's say I had a 1/3. So B is 1/3. I'm actually going to use that as a 3. Timesing things by 3 makes them bigger. So on my graph, I'm actually stretching. Is that okay with everybody? I know it's not a simple concept, but we have to find a way to kind of wrap our head around the fact that B does the same things as A, but it's clearly not as simple as A. There's like a lot more underneath there, okay? We are going to